everyone. My name is Anne Nahm, and I'm working at the Jülich Supercomputing Center in Germany. In the following presentation, my colleague Alex Upton, who is working at the Swiss National Supercomputing Center, and myself will introduce you to the Phoenix infrastructure, which is providing cloud storage and compute resources to neuroscientists. And we will present a few examples of neuroscience projects that are using the resources provided by Phoenix. The Phoenix infrastructure is built by 5 European supercomputing centers: CEST in Spain, CEA in France, CINECA in Italy, CSCS in Switzerland, and JSC in Germany. The IC project, Interactive Computing E-Infrastructure for the Human Brain project, is the first implementation project of the Phoenix infrastructure, and the project is running under the umbrella of the Human Brain project. And this diagram illustrates the concept of Phoenix. The Phoenix infrastructure is providing e-infrastructure services at each of the supercomputing centers that are made available to neuroscientists inside and outside of the Human Brain project and to European researchers at large. The resources provided by the Phoenix infrastructure form a basis for community-specific tools and services which can build on and or use the infrastructure, like the HBP collaboratory that is made available to users or other eBrains services. Now, what kind of services or resources are made available to neuroscientists by the Phoenix infrastructure? We offer scalable computing services, so resources on a supercomputer that are suitable for running, for example, highly parallel brain simulations or high throughput data analysis tasks. We provide quick access to single compute servers, enabling users to connect to running simulations on supercomputers and to analyze and or visualize their data interactively. The Phoenix infrastructure offers a service for deploying virtual machines in a stable and controlled environment, for example, for platform services like the HBP collaboratory. And in addition, data repositories are provided, on the one hand for storing temporary slave replicas of large datasets, and on the other hand for long-term storage and sharing of large datasets. All information on resources that are available or will become available soon is published on the Phoenix website. And with this, I will hand over to Alex, who will introduce a few neuroscience projects that are using the Phoenix infrastructure.
Okay, so hello everyone. Thank you to Anna. As she mentioned, my name is Alex Upton. I'm working at CSCS. And now we're going to have a look at actually what neuroscientists are using the computational resources for. So at the moment, we have almost 30 projects from HBP members that are making use of the IC resources at CSCS. We approximately categorize these based on the usage and the resource they're using. So we have what we call small scalable compute projects. So these are projects that are using up to or just under 5,000 node hours per quarter. Then we have medium scalable compute projects. This is between 5,000 and up to 20,000 node hours per quarter. And then we have the large scalable compute projects, which are using 20,000 and above node hours per quarter. Then we also have what we call cloud compute projects, which are making use of the Pollux OpenStack system at CSCS. What we should note that within these 30 projects, it's a wide variety. So this ranges from neurorobotics to cerebellum modeling to the neuromorphic computing. So it's a wide range of use cases and research fields within neuroscience that are making use of these resources. Next slide, please. So now in the following slides, we're going to look specifically at 3 examples of running projects. These are the full-scale hippocampus model, where the PI is Michele Migliore, who is based at CNR Computational Neuroscience Lab in Italy. Then we have the NEST Network Construction Simulation Project, where the PI is Hans Eckhard Plesser, who's at the Norwegian University of Life Sciences. And then finally, we're going to look at the neuromorphic computing front-end services, where the PI is Andrew Davidson at the Paris Saclay Institute of Neuroscience. as also mentioned in the previous slide, that the offering of IC Phoenix, it supports a wide variety of uses across multiple fields of neuroscience. So we're able to support many, many use cases across neuroscience. Next slide, please. So the first example we're going to look at is the full-scale hippocampus model. Now, the idea with this project is to develop the first detailed and realistic 3D model of the CA1 area of the hippocampus. And this is done in order to obtain fundamental insight into the cellular mechanisms that may give rise to cognitive processes. What should be noted about this, this project is it's a very novel contribution. As mentioned, it's the first attempt to develop a detailed and realistic 3D model. However, as you might have guessed in the description, this doesn't come without its challenges. In particular, if we look at the rat hippocampus CA1 region, we have approximately 460,000 neurons that we have to model. And when we look at the model itself, this then requires a minimum of 25,000 cores to run. To put these numbers into context, if you think that the laptop that I'm currently using, that I'm speaking to now, has 4 cores, that means that over 6,000 laptops would be needed to run this. So you can see that this presents a real computational challenge. Fortunately, with the IT resources, we're able to overcome this. And in fact, the scalable compute resources on the Pitstein as multi-core partition on the supercomputer were used in order to run this model, which we'll see if we go to now to the next slide. So if we play the video, we can see on the video here that on the right, we have the hippocampus, and on the left, we have the detailed CA1 region. And looking at this model here, this is actually simulating 0.5 seconds of simulation time. However, for 0.5 seconds of simulation time, this actually generates 1 terabyte of data. Again, to put this into context, on the laptop that I'm speaking to you now, I have 500 gigabytes of data, meaning that for 0.5 seconds of simulation time, it generates 4 times the amount of data storage or the data that I'm able to store on my laptop. And it requires 2 hours, 15 minutes to run on the Pitstein supercomputer. So it gives you an idea of the real computational challenge and how the IC resources help to resolve this. Next slide, please. The next project we're going to look at is the next network construction simulation. Now, as some of you might be aware, within the neuroscience community, NEST is a key tool for the simulation of networks. And the goal of this project is to test, benchmark, and optimize NEST construction and simulation for using large-scale cellular models. So this means really how the deployment and the performance of NEST at scale. Again, as you might have guessed in the name, you need dedicated high-performance computing resources in order to do this, because you need to see the performance of NEST when you benchmark, when you scale it up to many, many cores. So in order to do this, again, this can't be done on the local resources. For example, as I mentioned before, my laptop that I'm speaking from now has 4 cores. So again, to do this, we took advantage of scalable compute resources on the Pitstein supercomputer we used. And in particular, this allowed identification of a performance issue in NEST 216 that they were unaware of. So before they did this benchmarking, they were unaware that there was a performance issue in NEST 216 that was identified and then subsequently removed in later versions of NEST. If we go to the next slide, we can see the plot here that's showing the performance of different versions of NEST. And if we look at the orange bars here, we can see that we can clearly identify that there was an issue that's then resolved in the subsequent releases shown in the green and the red bars. Next slide, please. So the next project we're going to look at are the neuromorphic computing front-end services. And the goal of this project is to allow researchers to access the neuromorphic systems directly from the web browser. Specifically, this allows them to run network simulations on the Spinnaker system and emulations on the BrainScale S neuromorphic system directly from their web browser. Again, in order to do this, it presents a computational challenge. Specifically in this case, there's a need for a non-commercial cloud environment. So most of you might be familiar with the likes of AWS, Microsoft Azure, Google Cloud Platform, But for this specific use case, there was a need for a stable non-commercial cloud environment in order to deploy the virtual machines to enable access to the neuromorphic systems via the web browser. And in order to overcome this computational challenge, a cloud compute OpenStack resources on the CEST Pollock system were used. And if we go to the next slide, we can see screenshots of what this actually means. So we can see here that researchers are able to access the neuromorphic computing systems directly from their browser. In particular, if we look at the screenshot on the right, we can see the job manager, which allows users to see, for example, the status of jobs they submitted. Allows them to see the system they submitted the job to, the code they submitted, when the job was submitted, and who the job was submitted by. So it allows them directly to see this information through their web browser.
Okay, so if you now got interested in using resources of the Phoenix infrastructure for your research, you can get access to the Phoenix infrastructure via the Open HBP eBrains call, which offers the resources to neuroscientists who are in need of compute, cloud, and/or storage resources. With this call, European neuroscientists are invited to submit proposals for using these resources for research on topics in the broader scope of the HBP. So, for example, for projects that focus on the analysis of brain data leading to an improved understanding of brain functions, projects that build multi-scale scaffold series and models for the brain, or other projects that perform simulations of brain functions, and also projects on brain-inspired computing, data analytics, and robotics. The call and the details on how to submit a proposal are published on the Phoenix website, where you can also find all information on access for the different user communities. And in order to introduce new users and relevant audiences to Phoenix services and resources, we are also organizing a series of webinars and online trainings. On this slide, you can see a list of the topics covered so far, and you will find the full recordings of these webinars and also the presentation slides on the Phoenix website. The webinars take place roughly every 2 months and are announced on the Phoenix website via our Twitter account and also in the Phoenix User Forum. The Phoenix User Forum offers current and future users the opportunity to engage directly with the IC Phoenix team and technical experts. And we provide there further documentation on Phoenix, the offered services, and we announce events where Phoenix is presented and open calls, etc. So the details are published on our website, and if you would like to register already now, you can scan the QR code, which is shown here. In case you have any questions about the Phoenix infrastructure and the offered services and resources, do not hesitate to contact us via our coordination email address, which is shown here, or also via the contact form on the Phoenix website. And if you would like to receive the latest news on Phoenix and all the call announcements, follow us on Twitter at PhoenixRIEU. And with this, I would like to thank you all for your attention, and we are happy to answer your questions. Okay, so now we have time for questions.
And I see we've already received a question. So we received a question which is, are there fees or other costs for Phoenix users? So the answer is no, there are no costs. The resources are currently allocated free of charge. And this is based on an assessment of the merit, of the excellence, shall we say, of the proposal, of the project that's been proposed. So the takeaway is no, that it won't cost you anything. Do we have any? Yes, okay. Next question we received is, when a project proposal has been approved, for how long are Phoenix resources granted to the project? So once the project has been approved, then resources are granted, typically they're granted for a period of 1 year. However, if a project needs to use them for longer, they can actually submit a renewal process proposal. And we actually have examples of projects that they had resources allocated for a year, and then they asked to renew them for longer, and now they're currently being allocated for a longer time. So yes, typically it's at the start with their year, but there is a possibility to extend this for longer if needed. Okay. Yeah. Next question. Maybe Anna, you could answer this one.
Yes. So the next one says, how long does it usually take for submitting an application until the resources are available to the project? So the submitted applications are evaluated in a peer review process, and they undergo a technical assessment and also a scientific assessment. And this evaluation process usually takes 4 to 6 weeks. However, if only a small amount of resources is needed by a project, applications can also be approved in a shortened procedure, which takes about 2 to 3 weeks. Okay, are there more questions?
Okay, so maybe we can, if there are no more questions, maybe we can finish the session. So again, thank you everyone for attending. Hopefully you found this session useful. Again, if you have any questions that perhaps might come to you later, or maybe you're watching later, feel free, of course, to contact us. Also check out the website, which is phoenix-ri.eu, where you can also find some additional information. And yes, I think that's it from us.
Yeah, thank you.
Okay, thank you everyone.